Here's your team viewer. Naja, are you following us? Just look, have a look to the screen. I'm going to download this on Muhammad, so you can follow us. Okay, where is Muhammad? Where is the Aspen Heises in your Muhammad? The file you downloaded on where is it? Yes. No. The one with the 10 GB, which I sent the link for it. Yes. This is a company standard, which we go here. Hysis 11, same version for me. Please download and install it. Okay, it will take a time to download it, Muhammad, from your side. So, Naja, do you have this link? Download this one. Okay, Muhammad, when it's finished, just on me. Okay? I will close the team viewer now. Naja. Naja. Hello, Naja. Yes, tell me, do you have a team viewer? Did you install? Did you download the link? Okay, just stay with mute, please, and we're going to start. When you download your team viewer and you have Hysis, we can use the break to install it. Okay? Okay. Can you make a note, please? Thank you. Okay, let's start our presentations. Last time, stop with, we have some gases here. We need to pressurize this gas to reach the main center processing facilities with a high pressure. That was our task last time. This BFD was shared with you on basis that we're going to develop a BNID for such equipment. We need a BNID for this descender, BNID for the separator, BNID for the compressor, BNID for the surge drum, and BNID for the pumps. The basic thinking way how a process engineer would think about this project is first to develop the simulation material. The first step of any project is to identify from the basis of design the amount, or not the amount, the heat and material balance. Heat and material balance is simply what rule the performance of all of this equipment. It will be the baseline for designing all this equipment. That's why we are interesting, all process engineers must be interested in learning how to develop heat and material balance using softwares like HYSYS or even by Excel sheets. Okay, let's share the basis of design so we can scroll down and understand what is interesting from our side for basis of design. Here we are. Going all the way. Here's the normal introduction about the company and our customer, which was in this case Wasco. Yes, who wants to speak? Okay, Naga, tell me. I don't get it anything. What do you mean? Viewer? Not able to download it? Use the link which I send it on the WhatsApp. Okay, there is a record for this meeting anyway. Once Muhammad download the folder from the SharePoint, we'll use the break to install the HYSYS software on his laptop, so you can see how you can do it on the video. Okay. Okay, now let's focus on how we are going to develop the BFD, the BNID, then we are going to simulation, hydraulic, and the design step by step. Okay, let's back to the basis of design which we have. Can you see my screen now? for the introduction. Perfect. What we are trying to do is simply, here is the introduction about the company and what we have, the field name, the first core field that we are trying to construct. We have some wells called first core 2, 3, 4, south first core 1, 2, 1, 3, 4. All of them are going to produce 20 million SCF. What we are trying to do is engineering, contract and scope of work is to perform a complete detailed engineering package for the first core compression station. We will build a compression station 1 by 20 million standard cubic feet for the compressor pump. So let's start. Here is a typical basis of design. You have all the abbreviations section, then you have the unit of measurement. It's different from client to client. When I work with E&I, they refuse to have the kilometers on the distance in kilometers. They always use miles. Pressure, they always use bars, and keep going the same way from client to client. This is not a big issue as long as stick with some system, European system or international system. Here are some applicable codes and standard for the ASME, for the ventilations, APIs, process administration and control, process analyzer, refinery control valves, and keep going all the way down where API 12J, oil and gas separator, and we are going to use this very much, how I can say it, we're going to use it many times. The same here for API 14E, we're going to use it many times. Why? In this one we're going to use for the original velocity calculations, which is coming on after a few minutes, and this will be on the third day or fourth day, I think, for the sizing of the separator. Keep going down. All these IEC standards from the instrumentation, ergonomics, ISO, ISA, for the graphic symbol, for the process display on the HMI, and this will include diagrams. We're going to tackle all of this. Okay. The first and important part for any process engineer is to define the battery limit. Why? Without defining the battery limit from your customer, you will not be able to close your project, even to define your scope strictly. Here, the battery limit was the inlet flow, I love you Naga wallah. Naga, I love your picture. I respect this. Okay, let's complete and we will go to this one. I just will explain the basic design, then we will switch to the PFD and BLID development. Battery limits, which you are going to define, is the inlet flow, what we will going to receive from the wells, what we are going to deliver to the piping network. Inlet flow is the production manifold upstream for school phase 2 compression stations, and outlet flow, and there is an existing 12-inch 20 kilometer pipeline from the client side. That means, let me share my whiteboard so we can draw something. Here we are. This means if this will be our plant, then what is coming from here is the well side. Then after the compression, we will end it up by have some gases, some liquid. Both are going to be mixed and sent to the pipeline network. That's what we are trying to understand. Here is what we're receiving from the wells. Here is what we are going to send to the pipeline. Is it clear for everyone? Okay. Let's go back to the basis of design. Process description. Raw gas feed from the wells to be received at the existing first Cooper Phase 2 inlet manifold via existing flow lines from the wells. We have a flow lines from the well. We are going to receive the gas, the condensate, and even the water. All the feed from the well. The gases then shall be directed to a new online sand removal unit. Okay. Let's see, Muhammad. We did our homework. What we are going to receive from the well is good, mashallah, Muhammad. Allah yanawar. Muhammad send also something good. What we are going to understand from this one, that when the reservoir engineering work and when we get the sample from the reservoir engineer, he told us that take care, this well will going to send you quantity of sand because of the formation underground. Then he will have some gases, water, condensate, and sand. Based on this information, when we are going to design this one, we are afraid from the sand entering the compressor. If the sand entering the compressor, it will damage the compressor. So we need to remove the sand. If the sand entering the separator, it will affect the separation process of the separator. That's why we need to remove the sand. So what we are going to do is we're going to install sand removal unit to remove the sand from the process fluid. As you know, sand is a solid particles. If we're going to a centrifugal process, all the sand will precipitate to the bottom, all the other fluid will go from the top. We're going to discuss this specifically now. Then the sand-free process shall be then separated into gas, condensate, and water in a new three-phase separator. Then we are going to separate the gas and the water and the condensate in a three-phase separator, such that the gases are compressed. Then we will take the gases and direct it toward the 12-inch 20 km pipeline after compressing it, and the condensate is directed to a new condensate surge drum. then pump it also toward the 12-inch 20 kilometer pipeline, and the water will go into the evaporation pot. That's mean we are going to extract gases and condensate from the stream, send it back to the network, and we're going to have a byproducts which will be the sand and the water. Controlling philosophy. We're going to discuss it deeply. Let's take it here. The feed to the plant is controlled to a three-phase separator after sand removal via a feed forward pressure control valve. We are going to speak about the control valves and the control loops, which one we are going to install in the separator and upstream or downstream in the separator. The levels inside the three-phase separator are maintained via level control valve. We're going to speak about this specifically when we are going to design the separator. Let me relief system last day. I will jump to the composition here. This is what we are searching for. The facility shall provide to process feed gas production as follows. We have a quantity of gas which is 20 million scf. We have a condensate rate for 1000 barrel. We have a water rate for 2000 barrel. We have a sand rate 20 kilogram per day. We have operating pressure 900 in the beginning of the project and 250 at the end of the project. Flow rate, design factor over design factor or design margin would be 10%. Here is the well fluid composition. As you see, we start with hydrogen, fill all the losses, which will be 0.001 by the end, which will give you the 100%. Muhammad Najah, take care about this one. This is the design case that we are going to have on our simulations. Here we have three different operating cases for this model compression. Both have the same quantity of gas. Both have the same quantity of condensate and water, but with different operating pressure, which will make a big problem with you. This means you have to simulate to make three simulation cases. And always take the worst one for your design. There is a set or rule of thumb for a process engineer. When you are design for the worst case. The worst case is the most dominating in any design. So the worst case here, are we going to have a high pressure or low pressure? I need answers. What will be the worst case? This one or this one? Which one? One or three? This is the worst case? Yes. What about you, Muhammad? Yeah, Muhammad. Yes, the question is, which case is the worst case? Check valve for doing what? I don't have a problem with this. My question is, which case we are going to simulate, and based on what? High pressure will increase the separator efficiency or reduce it. Biological thinking. I don't want you to be expert in separator. Increase the volume of the liquid? No. Increase the volume of the gas? Yes. Let me explain it. Why, Naja, we are interesting to understand this, because let me move this all of this first. Just let's click a new one. Okay. Here, sorry. Here is the separator. Entering the separator and the outlet of the separator. If we entering with 250, this mean this 500 maybe 900. 250 will help in a better separation. So the purity of the gas will be good, and the purity of condensate will be good. Good mean more than 95% on each side. But in this case, if we have here pressure safety valve, this mean as long as the pressure increase, the inventory of the gases here will increase. Why? As the gases is a compressible, as the pressure increase, the amount of the gases will increase. So sizing this pressure safety valve should be based on the 900. But as the pressure increase, the performance of the separator decrease, and as the pressure reduce, the performance of the separator increase. So for operating pressure 250, you are going to use to size the liquid hold up section inside the separator, but the 900 we're going to use it for the pressure safety valve. So in this case, both 250 and 900 representing the limits, one for liquid, one for gas. So both cases are critical for us, and we need to simulate to understand how much liquid holdup will be here, how much gas compressed and the inventory will be here on the 900 psi. That's why we're going to simulate both. Is it clear for everyone? Okay. Well, let me write it here. BV equal nRT, right? T is a constant, it's ambient temperature. R is a constant, is normal, constant actually, and number of moles didn't change. So B in reverse relation with the volume. Here is a B increase, and the volume of the gas need to catch how much pressure increase. So back in here, then you have the compressibility of the gas. You will have all this portion compressed portion of the gas, then another compressed portion of the gas, then another compressed portion of the gas. So when we are depressurizing this high pressure gases setting from 900 to atmospheric, which is the outlet of the pressure safety valve, from 900 to atmospheric, there will be a lot of depressurization, a lot of inventory inside the same volume, which is the separator volume. On the other side, 900 to 150 here will have a less volume. This means when we are going to depressurize this separator to the atmosphere, 250 will be the gases which you have, the 250 psi, will end up first fast compared to the 900 psi. This 900 psi will take a longer time compared with this 250 because of the inventory in here is higher due to the compressibility of the gas. On the other meaning, when you have a cylinder and your car cylinder, and you're going to make the maximum of this car cylinder, the car cylinder is traveling to compress all the fuel or your fuel, which is converting to gas with the air until it reaches the compression ratio, the proper compression ratio, then it starts to make the ignition. It is the same way of the compressibility. You got it, Muhammad, or I think you didn't get it, right? Yes, it is what we are typical heat and vapor balance. What we are trying to say here. Two cylinders have the same volume, BV, so equals Z nRT. Remember this law from the university? Yes, this Z factor is called compressibility factor. Gas can be compressed, right? If we have a gas here, this cylinder can move till this point, but we have a liquid here. If we have a liquid here, this one will not be able to move 1 inch. Why? Because liquid is non-compressible. Are we agree on this principle, Muhammad? Because gas is a compressible, so we have this Z factor. Compressibility, when we have a fixed volume, a fixed nRT, this means compressibility is in a direct relation with the pressure. When you increasing the pressure, you're increasing the squeezing of the gas, increasing the compressibility of the gas, which means that this Z factor will increase, which means in a constant volume, the amount of gas will increase as the pressure increase, as the compressibility increase. So why we are interested on this? Because in a normal depressurization curve, we're starting here with the pressure inside the spray. If we have, here is the 900 and here is the 250. For the 900 take a longer time to depressurize compared with the 250. So we have to design for the worst case compared with this 250 case. Why on the 900 we have longer time? Because we have a higher gas volume compared with the 250. Even one of the debottlenecking studies, when you're doing a debottlenecking study for your plant, you always see the maximum inventory and how much gas is liquid inside your equipment, and based on that you decide to increase or reduce. You got it, Muhammad? Muhammad? Back to our basis of design. Based on this, we are going to make the design cases for this two, case 1 and case 3, to make sure that we are covering these cases. Then we have all these other curve areas. I share this folder with you on WhatsApp. Did you receive it? I don't get it. Did you receive this one, right? From the SharePoint. If you open it, here is all the project. If you go, for example, Transmittal 13, you will have all the PNIDs. Transmittal 4, for example, not 4, let me 5. Plant layout philosophy. 7, you have the electrical design specifications. 8, publication. 9, surfaces. Here we are. This is transmittal 2, Muhammad. You will have the heated air balance and BFD. Transmittal 1, you will have the basis of design, which you are reading from it now. You already have the full project on your share folder. Everything every transmitter. You get my point, Muhammad? When you open this one, here we are, you will have this transmitters. Transmitter 2, you will find the heat tap balance and BFD. Are you able to see? Open transmitter 2. Here is the heat tap balance BFD. Open transmitter 1. TML01. You will have the folder which you are reading from it now. Right? What is the same? Yes. It is a different revision, Muhammad. Only, I got your point. Let me clarify for this one. As you can see, I am searching on all transmitters, trying to find where and the date of the updating the revision. Here we are, Hamad. Transmitter 22. Open it. The 27 transmitter was first submitted to the client, then we have a comments on it, then we send it back 22. You're welcome. It is the deliverable list of the project. Transmitters we are sending to the client, and every transmitters have its own document in a Word format and PDF format. Then we have the CRS comment return sheet from the comments from the client. Then we have the send it back to the clients for approvals and keep this cycle going, so it is easier to track it this way. You're welcome. Naja, we are still with us. Are you following? Okay, perfect. Okay. Naja, open transmitter 22, basis of design. Then hopefully this time ISIS will not fail us. Go Go to page 23. Okay. Can everyone see my screen now? Is it white on the background and we have gas, condensate water? Can you see this one? Gas, can you see the gas word and the blue arrow? It was not clear last time. Is it clear now? Naja, is it clear for you? Alhamdulillah. Was not clear last time. Yeah. Okay. Naja, open page 23 and start to say for me the operating conditions and the gas composition we are going to receive. From the first case, you were going to give me the first case. Muhammad, you're going to give me the third case. Muhammad for the 900, Naja for the 250. Okay? Okay, starting with you, Naja. Tell me, what's the temperature of the gas we have? Let's make it from the beginning, because I think the beginning would be good. Here we are. Yes. The temperature. Are you seeing my screen? Because I opened another screen. Yes, it is a gas and empty under it, right? Okay, tell me the temperature. Centigrade. And the pressure is? Yes. PSI, right? Okay. And the flow rate is? (20 standard cubic feet per day). Okay. Is it now going to be green? Is it green now? Do you see the green tab below? Yes, based on the composition which I already put on the last time. Do you remember when I was asking Muhammad to tell me the composition and it was not shown on your screen last time? I already installed this composition. You have the hydrogen is 0, H2S is 0, CO2 is 0.005, right? Nitrogen, methane, ethane, propan, butane, and keep going. Once we define all this, I just will tap close. Then we have the sorry. Here. Okay, define the ensolver. Tell me what's the meaning of enthalpy. Hello? Naja? Naja? Muhammad. Where is Naja? Naja disappear? Naja, are you following? Yes, don't mean the meaning of the enthalpy. What is the meaning of enthalpy and entropy? Here, pause. Yes, it have to be negative. The question is, what is the meaning of enthalpy? Yes, this is minus very little amount, minus 7.9 till multiplied by 10 to the power of 4. So it is basically 0.00079 minus, which is almost 0. But anyhow, it is still minus. Why it is a minus? Is there any enthalpy coming in a minus? Yes. Which enthalpy? The enthalpy of the gas. When the, what's the meaning of enthalpy by the beginning? In the beginning, which is the measurement of all the energy inside the system. The kinetic energy, the potential energy, what is the other one? The pressure energy, which is the first law of the thermodynamics. What will happen if we're going to increase this pressure like 500 psi? Is it going to increase? Molar enthalpy is still negative 500 psi. Why it's not going? What I'm doing? Sorry. Just 500 psi. Is it still my negative? This means the pressure will increase the enthalpy here. Yes, but if we're going for the temperature, it is still negative 100, negative 50, negative 250 psi. I just working with the numbers to make sure that every time we saying the enthalpy, let's 50 million, instead of increasing the quantity of the gas and make any change. What this give a clue for you, Muhammad, for you, Naja? Tell me, what's the difference? What's mean the molar enthalpy? Why the enthalpy here is negative compared with, let's say, the mass enthalpy and the mass entropy? Here the mass enthalpy is also in negative. Yes, let's keep it here. Mass enthalpy is also in negative. Kilojoule per kilogram. It is almost minus 3,827 on negative signs. This is the mass enthalpy. This is the how much enthalpy, kilojoule, we need for kilogram to make this gas in the vapor phase. Is this the gas in the vapor phase? It is in the vapor phase. It is almost a vapor phase. Why we need this negative signs? Do you know, Muhammad? If we decide to make this gas on a liquid phase, we will need, for each kilogram of the gas, we will need 3,827 kilojoule of energy to convert the gas to the liquid phase. Most enthalpies figures in the thermodynamic tables are coming from the liquid side. So when we have a stream like this one on the gas side, it is the HYSYS will search for the other, how I can say it, other for the other phase of this composition on the liquid side, and start to calculate based on the mole fraction how much it take energy to convert it from this gas side to liquid. From gas to liquid, you have to take the energy from the gas. From liquid to gas, you have to give energy. So when you have a liquid, like, I will close this, Naja, 1 minute. When we have a liquid like condensate here, for example, I want a pure liquid. It's the same here. When we have a pure component like this one, and you need to convert it to pure component in liquid phase, and you need to convert it to a gas phase, you will simply added energy. This will be adding energy will be on a positive sign. Removing energy will be in a negative side. That's why we have this negative sign. Did you work with the first law of thermodynamics before, Naja? Naja? Yes. And did you see the application of the first law of thermodynamics? Did you have any steam traps, steam boilers? It is very clear there. The gas on the steam always have a negative mass enthalpy, always have a negative molar enthalpy. Removing it, taking the energy from it, converting the steam to a liquid, you could get the positive signs. The good part of the HYSYS is that we have the gas, the condensate, and the water side. That's what's coming. All these three is coming from the well. Can we simulate the sand on the HYSYS? No, we cannot. We cannot simulate sand on the HYSYS. So we will end up by having the gas, the condensate, the water. All the three is mixing in the pipeline before they reach the plant inventory. Yes. So what we are trying to do now is to get the full composition from the well. If we go to the composition here, we should be able to see the composition which is coming in our basis of design. Where is the methane? Ethane is 0.48, whereas the hexane is 0.04. That's all what we have, where the water is 0.4. That means we have almost 0.4 water, 0.48 methane, and 0.04 will coming on the liquid phases. Then what we are trying to do, Naja, we are going to move to the sand removal. We cannot simulate sand removal on HYSYS. What we are trying to simulate, we are going to simulate the three-phase separator first, then the surge drum, then the pump, then the compressor, and each one will be on a deep. So pressing F4 to get the unit operation here. What we are searching for, a three-phase separator. You see my screen, right? معايا يا محمد؟ Okay, perfect. Drag and drop. Then we have this one, what will be the inlet from the gas well. It will be 3-phase separator. What we are going to release, we will have gas to compressor. Then we have the heavy liquid will be water to evaporation pond. Then we have liquid, or not liquid, will be condensate to surge drum. Did you see what we have, Naja? Here is a 3-phase separator. I use the typical physical properties of the stream from the well to define the gases from the upstream, the condensate from the middle, and the water from the bottom. Here is the gases to the compressor. It's coming with this right click and show table. Show table is a property here to show how much pressure and temperature we have for this stream. We have the gas now coming out of the compressor with a pressure almost 16 bar and a temperature almost 47 bar. Then these gases we want to compress it to be how much? To be 900 or 1000? Can anyone reply to me? It is a tricky question. Yes. Now I am going to install a compressor here. Here's the compressor. I am going to install it. The question is how much pressure I want this compressor to compress the gas to the outlet. What is the discharge pressure I want from this operation, from this compressor? Yes, not 900. What? Bravo. Excellent. How you got this number? Totally right. It is called our boundary limits. Here is the inlet boundary limits, and we need the outlet boundary limits under my mouse. So what we are going to do is, here is the compressor. Here is what is the inlet, gas to compressor. What will be the outlet? Will be gas to piping network. Are you follow Muhammad? How much energy we need? Let's name it Q1. He will ask for unknown duty. go for these parameters. It is a centrifugal compressor or reciprocating compressor, or with gas or screw compressor. Because it is a high pressure, we're going to a reciprocating compressor. Then we have a delta B, or pressure ratio, for the outlet. What I prefer is, I don't know, I can calculate the delta B from 100 for 1100 psi and 250, or I simply, because I don't want to calculate or use my mind, so I will double click here, saying here 1200 psi, right? Then automatically the HYSYS calculate the delta B, which is almost 85.61 bar G, and the compression ratio, which is 4.4, and he calculates the duty for the compressor. I didn't get it. The HYSYS get it. What I know is, I want the outlet from this compressor to be 1100 psi, right? From my basis of design. From my basis of design. Who's speaking? Which one? Who's speaking? Muhammad? Naja? Yeah, okay. So, what I did is, the info I know, the information which I know, that I need this gas to be 1100 psig. So I insert it here, closed. Based on this, HYSYS makes the calculation for the compressor, telling me that if you decide to have a reciprocating compressor, and the delta B will be 58.61 bar, and pressure ratio 4.4, which is a very high pressure ratio, then you have a duty almost 1592.4. Basis on that, you have a polytropic efficiency 77.9. Normally, Naja, normally Muhammad, we are trying to have efficiency of all rotating equipment, anything above 70% efficiency is considering high. What the maximum we can achieve from this efficiency, from this rotating device's efficiency, the maximum I see is 80. Normally we are designing for 75. The question for you, Muhammad, the question for you, Naja, why we didn't achieve the 100 duty, the 100 efficiency for the rotating devices? I don't hear it. Can you repeat? Just to repeat what you said. I don't hear what you said. Your voice was not clear. But if you can hear me, normally the 25 is going for the friction, going for the rotating parts, because of the rotating parts are not able to transfer the 100% efficiency. All the losses for the heating, or the losses for the friction, or the losses for the gearbox inside the rotating parts will cost you the 25% we are speaking about. Okay, let's continue. We need to finish this simulation before we take our break. Then, here is the first output from our plant. We need to make from the BFD, we need to make this condensate will go to surge drum, which is typically a two-phase separator. Here we are. It will be called surge drum. What's going to enter it? Condensate. Here's some vapors going to be outed, gas to flare. Then we have condensate to piping network. Here are some gases, small amount of gases, which is almost, as you can see, molar flow equal 0. Then we have the liquids here. What we want to do is to pump this liquid with the same pressure for the gas. So we're going to use spring pump. Here is the pump. We're going to condensate pump, inlet, condensate to piping network, condensate to piping, and we will name the energy needed to Q2, so the ICEs will start to calculate it. The question is unknown duty, delta B, pressure issue, unknown duty. Adiabatic efficiency is almost the same as the compressor, which is 75%. Because I don't want to calculate myself, so I will click it here and go here, saying that the condensate to piping, the same philosophy, 100, 1100 PSI absolute. Once it is calculated, the pump is already defined. The pressure ratio is 4.4. The duty is almost 15.3 kilowatt, and the delta B is almost the same, 85.61. Here is the condensate, here is the gas. I want to send both of them to the network. Then I will add a mixer to mix both gas to piping and condensate to piping. Mixer, I will inlet gas to piping and condensate to piping, then outlet feed. Here we are, our simulation for this nodal compression station. here is the outlet for the plant, here is the inlet for the plant, here is the compressor, here is the pump, here is the surge drum, here is the three-phase separator. Anyone want to ask any question? Hello? Houston, anyone listening to me? Your voice is breaking. And I says we do what? Battery limit condition is what we see here is what we receive for the client. Here is the objective of the client. What is happening in between? What happened in between is our design. The client wants this outlet feed and he has this input. We always design. In the feed stage, we tell our client that we can achieve your objective by this list of equipment. And once we have the PFD, once we have the process flow diagram, which is similar to this, can you have a snap look? Three-phase separator, surge drum, compressor, pump. If you allow me to share, let me share the process flow diagram. Where is it? This is the same. Here is the inlet condition, here is the three-phase separator, here is the compressor, here is the surge drum, here is the pump, here is the outlet condition. You got my point, Naja? Once we have all this in our hand, the first discipline, the first task for a process engineer is to simulate the process flow diagram, and based off the simulation results, every discipline will work after it. How does this mean? Which discipline we are speaking about? The hydraulic discipline, which we are going to learn today. Let me clarify something. Look, Naja, for example, if you consider, let me draw here. If you consider this pipeline between the sand removal and the separator, what will be the size for this pipeline? What will be the controlling philosophy for this one? You got my point? This not can be solved until we have the heat and material balance, because from the heat and material balance we will know how much feed, how much flow is entering this pipeline, how much gas is outlet from this separator, how much liquid condensate and liquid water coming out of this separator. Based on this heat and material balance, this simulation reports, we are going to develop the selection of the piping size first. Second, when we have the selection of this piping size, we are going to select the piping material on the composition. When we have the composition, we will know the material. When we have the flow rate, the pressure, the temperature, we're going to select the size of the pipeline. Here is all this piping. When we have all this piping, we will have a list for all this piping. This piping list, we will list all the to from. Let me share it with you, because this will be your next assignment. I already shared it on WhatsApp. Do you see it? Which is called line designation table. Here we are. This will be your next task. Here is the fluid type, the diameter, the pipe specs, line number, from, to, operating pressure, design temperature, total pressure, type of test for the hydraulic calculation. Do you need insulation, yes or no? The number of B&ID, tie-in number, and keep going. You get my point? Hello? Yes, that we are going to learn today. The hydraulic and the basis of hydraulic, how we are selecting the size, how we are making sure that the size between the equipment are correct based on the equipment needs. Okay, we will take yes, tell me, Muhammad. Yes, and simply depending on the ASME, we're going to work with it today. Oh, welcome. What's the type now? Okay, we will continue on 10. Okay, 940 is you're in Saudi Arabia, right? Right, Muhammad? Okay. We will continue on 10 at your side, and Naja 11 at your side, if I'm not mistaken, right? Okay. Yes, just take a cup of coffee and we will come back. You're welcome. Here we go. Okay. Here we are. Okay. Muhammad is not completed, Muhammad. It is 10 GB. How come? Yes? Oh, it is 10 GB. Open it. You see, have a lot of things. You have here on track. You have the license manager. A lot of things, tools. This is not shown on your desktop. Ah, sorry. Okay. Get. I'm opening another website, Muhammad, so you can. Look, Muhammad, you got my point? Okay, it is password 123. When it next break, hopefully it will be finished. Then we're going to install it. Inshallah. You're welcome. Anyone make before hydraulic calculation? Hydraulic. Did you calculate before any hydraulic? Did you make any before any hydraulic calculation? Yes. Perfect. perfect for me. Muhammad, one day when you was on your shift and one of your operators coming to you saying that who is this operator? Who is a pump? Engineer Muhammad, we have a major problem with one of the pumps. It is always cavitate, which is coming from cavitation. We always have a cavitation with the pump. This vessel operating condition didn't change since 20 years. This pump is running for 20 years. And the system didn't change for the last 20 years. But now, we have a cavitation for the pump. Always cavitate. The question for you, Naja and Muhammad. What will be the possible causes for this pump not to run? I want to understand your imagination. This system this is a separator and this is a pump. This system was working for 20 years. A very good condition. Now, your operator is coming to you saying that Muhammad, please, we have a cavitation problem with the pump. Always a cavitation problem with the pump. What will be the potential causes for this pump cavitation? What else? Good. What else? The same level, same operating condition, didn't change. Okay, composition change may be one of the problems. What else? Same flow rate, not changed. Yes, totally, it is a real example. Is ambient temperature. More temperature mean more volatile components near vapor lock to the pump, not cavitation to the pump. Hamad, I miss your voice. I know. depends. Yes and no. Okay, let's start. To make this pump work, we need to have net positive suction head available much higher than net positive suction head required. What I am asking here is the basic principle of hydraulic. Simply, if we have a liquid here and we want this liquid to go all the way in this pipeline till it reaches the pump section, right? Without any laws, I just make a basic understand. What is pushing this liquid to go all this way to the pump? The pressure here and the level here, which is rho GH, right? What is preventing the liquid from going to the pump is the differential pressure inside this pipeline, which is coming from the friction of the internal surface of the pipeline. Normally, if you served my links or my file which I intended for the BP and Shell and ExxonMobil, you will see that always ExxonMobil and Shell have this quantity minus this delta B is used to calculate the net positive suction head available. If you're working for a PP, when you're making the calculation for this net positive suction head available, by client request you add extra 1 meter to this net positive suction head available. If you're working for a BP. If you're working for a Shell, you will add 1.3 meter. If you're working with E and I, you will end up by 0.75 meter plus the net positive suction head available, which mean that this vessel will go up by 0.75 meter. This mean in our construction we will increase the height for this separators concrete supports to be higher by 0.75 meter, or simply we reduce the pump level down to 0.75 meter based on which client you are working with. That is difference between the clients we are using to see. Normally when the operator comes to you with this problem, that saying that please this pump is cavitating, normally we will go with saying that we will check the net positive suction head of each one. We will check the net positive suction head equation. We will check that the pressure is the same, the level of the liquid is the same, and the strainer okay, we have a problem with for us. He tried to sign to the okay. Just I'm trying to make phrase entering. We'll see if I can. How we can allow someone to enter? Anyone know? Mark, we need your assistance, please. Faiz, welcome back. Faiz. Faiz, are you here? Enter. Faiz. Hello. Okay. Face texts me on WhatsApp that he was trying to sign in 20 minutes ago, and he is in now, but I don't know why he is not speaking. There he is. Okay. Let's go back. Do you see my screen, right? Hello, Hamad Naja, do you see my screen? Okay. I hear, but you can't hear me. Okay. As long as you hear Faiz, that's good. If there anything, just text me on WhatsApp, no problem. What we are trying to say, we starting this I will release from access from mobile. Okay, perfect. One time we have a separator, then we have a pump running for 20 years. I will just say quickly for Muhammad, for Faiz. Then your operator come complaining that this pump is not running good. It is have a cavitation phenomena every time. When we calculating the net positive suction head available compared with the net positive suction head requirement, we always required to have net positive suction head available higher than the net positive suction head required to be very, very less compared to with the net positive suction head available. In some companies like BB have 1 meter, and in Shell 1.3 E 9.75, which means that you're going to increase this separator height on your construction, on the civil support for this separator. You're going to increase the height of this separator by 1.3 or 1 meter or 0.1.75 depending on your client. Then you have the pump here. Normally what we are trying to say that what is pushing the liquid all this way till it reaches the flange of the pump, the skid of the pump. The pressure here above the liquid, the weight of the liquid levels, which is rho GH. What is preventing the liquid from reaching the pump is the delta P across the pipeline. So normally, no, is there anyone speaking? Phase. Alhamdulillah. Welcome back. You're welcome. Then, what we have is a net positive suction head available, net positive suction head required. We check the pump, the pressure from the trends, we check the level from the trends, we make sure that the composition entering here is the same from the lab department. Then we will start to make the calculation for the available net positive suction head by adding this and this minus this term. By the end of the day, you will find that 99% after 20 years of operation for this equipment, this term will be higher than these two terms, which give you a net positive suction head available on a negative value. This means the pump will cavitate. So basically making this pipe shorter, reduce the length of this pipeline, would make this delta B reduce. In this case, the net positive suction head will be a positive value back again. If not, that cannot happen. You will have to replace this suction line with a brand new pipeline to have a friction losses less than what we have after 20 years of operation. You got my point, Naja? Yes, 99% it will be the section line. The friction losses in the section line increasing the term of delta B, reducing the net positive suction head available, and makes the pump cavitate. This is all. It is not a choking. It is a friction losses. Choking is meaning that there is something closing. Maybe a valve, manual valve, or a strainer. You got my point? Section line is what? Totally right. Yes, that's what we are going to speak. Let me start from this here, then go into total standard to see the reference for each one. The liquid line normally will have the velocity or flow rate of the fluid, the viscosity, the roughness, the density. All these four factors affecting the size of the pipeline. Is there a velocity you are trying to keep on the pipeline? Yes. In each pipeline? Yes. Depend on what? Depend on API 14E. What's API 14E? We are afraid from a velocity called the erosional velocity. Erosional velocity here normally from the gases we are trying to be lower than 30 feet per second. For the liquid we are trying to be less than 10 feet per second. Is there a reference for such numbers? Yes. What is the reference for such number? API 14E. ABI 14E. You got my point? Okay. On other terms, ABI 14E, I will open it now. Then I open Total Standard to see the difference between each camera. Okay? Yes. What is the question? The question, if we want to have a mixture between gas and oil? Yes. Okay, can you give me 5 minutes and I will explain all of this for a liquid, for a gas, and for a mixture base. Okay? You're welcome. Just to plug my external hard to bring the ABI 14E and then for the total. Where is it? I can't find it. Okay. This one. Okay, are you ready? Let me share this one. Where is the Here we are. Can you see this one, please? Hello? Take care. Here is the pump suction. Here is the delta P per kilometer, the normal, the maximum, which is accepted by Total. Here is the maximum velocity for the 20-inch pipeline, for 18-inch, for the 6-inch, for the 2-inch. 1.8 is acceptable for the pump suction. For the pump suction. unit lines 1.8, 1.4, 1.6, which mean if we are making the same plant we are doing for a Total, and we want to connect a certain quantity of fluid between the three-phase separator and the surge drum, which we did on the PFD and we did it on the HYSYS. And we have a quantity, let's say 1000 barrel per day. Who is waiting on the lobby? I think no one is waiting as well. I turn to the menu to see who is waiting. Sorry, it is someone of the meeting of the lobby. I don't know how to make it. Mark, there's a message coming saying that there's someone on the waiting lobby. Can you just... Naga, you are looking with 2 accounts, right? No problem. I was like, I don't understand who's. Okay, no problem. Keep it. Just focus with me. No problem. Keep the 2 accounts. Just we have now unit lines. We have a bomb discharge. We have a water lines. We have a boiler feed. Each one of them, we have a recommendation from Total as a maximum velocity, as a delta B for each one. We will learn how to make this calculation by using the Excel sheets from Wally Parson today, and how to use it with a pipe segment on HYSYS, so we can judge the hydraulic between the pipelines. Okay everyone? Where is the contradicting? I don't get it. Yes, the delta B per 1 kilometer. Yes. Why they are contradicting? Yes. That's what we're going to see from the Excel sheet and from the Aspen HYSYS. Now let me share with you the API 14E. Let's open it. Here we are. I will jump to the original velocity. Here we are. This is the sizing criteria for liquid lines. Where is the average liquid velocity? Look, Muhammad. Here is the source for these guidelines from Total, and the same for BB, and the same for Shell. This is the original of all of these guidelines and specification for big companies. The velocities equation come from this one. Average liquid flow velocity feet per second equal 0.1 equal 0.012 multiplied by the liquid flow rate in barrels divided by the diameter. Okay, here is the pressure drop calculation. Here is the Reynolds number. and the Moody friction. All this I will send it to you Excel sheet, making all this calculation easier for you. The most important part for me is this one. Here is that's coming from API 14E. Here is the nominal pipe size, the globe valve, the angle valve, the swing valve. This is the delta B, most common delta B for everyone. So when I clicking on a globe valve on HYSYS or on an Excel sheet for a Wally Parson, for example, angle valve, you will have all these constants on the background, thread and welded, all this constant on the background. Pipeline, half inch, the same, and all on the background, which is the Moody factors for the calculation. Is that what we are trying to do? Let's focus so you will not get lost of me. What we are doing now is we have a two reference for the velocity and for the limitation. Total velocity, total limitations first, which is the velocity and the pressure, and from API 14E we see the equation there and there. What we are going to do now, let's assume a practical example. Let's assume that a flow of crude oil in a gathering system is, let's say we have a 10,000 barrel per day. The transfer pump has a charge pressure of 70 psi. We have a pump which sending 10,000 barrel per day with a pressure almost 70 psi. He's saying to you that additive wells are drilled which result in pumping rate. Then he increased the pumping rate by 15,000 barrel per day. What will be the pump's charge pressure have to be? Pump's charge pressure is a pressure drop in the discharge piping pressure at higher flow rate. Simply increasing the flow rate of the pump will reduce the discharge pressure. So using this equation, P final, which is the final pressure drop, equal B initial multiplied by the initial flow rate by the final flow rate to the power of 2. You will get that when we have 200 flow meter unit, 100 flow meter unit, 400 flow meter unit, you will get the delta B for 100 was 1 unit, which 1 psi, for example. Then if we have the 200 will be 4 units. If we have a 400, which we are tripling the flow, or making 4 times, power of 2 make it for 16 times, which means that if we double the flow, we make 4 times the friction losses. If we make 4 times the flow, we make 16 times the friction losses, which can be demonstrated by these numbers. The initial pressure was 70 psi, the final flow was 15,000 barrel, the initial flow was 10,000. This means the pump's charge pressure now is 157.5 psi, which means that if we want to keep the same flow rate, we need the pump to be 157.5, making after 10 years flow drop to 1000. What will the pump's charge pressure? If now we starting by 10,000, ended by 15,000, we will need a discharge pressure of almost 160 psi. After 10 years low, drops, we coming back again to 10,000, then we will need to have final pressure equal to 131.1. If we start 70, 10,000, then we have 6,667 barrel per day to the power of 2 multiplied by 10,000. Then we will end it by 31.1 psi. Is it weird example? Is it hard example or smooth example for you? Yeah, it is for liquid now. If we have a pump, we only deal with a liquid. If we have a feed, if we have a feed from the well, we have a gas and liquid. Yes. What we have here, the square, here is applicable for gas, gas and liquid mixtures, anything. You got it? You're welcome. Okay. For hydraulic, increasing the velocity, increasing the density will increase the pressure drop. It is a linear relationship between the pressure drop and the density. As long as we increasing the density, as long as we increasing the pressure drop. Okay. For example, a piping system designed for water at a flow rate of 1000 liters per minute, 260 GPM, gallon per minute. This flow rate have a pressure drop of almost 6 psi or 40 kilopascal. What will be the pressure drop at the same flow rate if the line is used for propane, which is totally different from water, which have a relative density of 0.5 compared to water. Zooming in here, the pressure drop for water was 6 psi. The relative density of propane is 0.5 multiplied by the pressure drop will give you 3 psi. The formula saying that determine the pressure drop in piping through which liquid flow. Liquid Muhammad, take care, is pressure equal pipe factor, which is depend on the piping material, friction factor, depend on the viscosity and the piping material, length of the pipe, velocity inside the pipe, liquid relative density, and the pipe diameter. All these calculations is used to determine the pressure drop inside the pipeline. Is there anyone who is doing the calculation by his hand? No. What is really done in engineering firms is junior engineers making it on HYSYS software. Chief engineer revalidate this calculation through Excel sheets. So, for example, I will not get this one. I will jump to the HYSYS. I'm not jumping to this paint point. Let me share this screen with you, and we'll make a practical one to make it easier for everyone, because I know practical is much easier. Muhammad, Naja, you will do it yourself. So please focus with me. We was assuming that we have our plant. Here is the well coming. Here is the product, which was gas plus condensate, right? Hello? Okay. The hydraulic we're going to do is for this pipeline, which we will name it 1. Hydraulic for pipeline 1. Assuming that this point is, here is the Christmas tree, here is the pipeline, here is the choke. The point after choke, we have a pressure almost 900, temperature almost 50, and flow rate equal 20 million scuff. Okay, this is the initial point for your site. Here we are. I make it more black, more bullet for you. Then this pipeline isometrics take care Naja. We are now speaking about the piping isometrics from the layout. It's moving like this one. It's moving like this. Then he going up. Then he moving like this. Then he go down. Then from here moving like this. Then with angle moving up. Then he moving like this. Another angle. Then he moving vertically. Then he making the tie into the plant. I'm a bad drawer, I know. Sorry. So this was, for example, 20 meter. Then he jump up for 2 meters. Then he have 90-degree elbows. Then he have here like 5 meter. Then he go down like 14 meter. Then he move like here like 50 meter. Then he have this angle, wide angle 135, which is like 7 meter. Then we have this angle, and he have like another 50 meter. Then he went up 18 meter. Then he have this pipeline 5 meter. You got it? This is called the piping isometrics. The piping isometrics is very hard. Why? Normally on, let's stop this one and share this one. Normally when we have this general arrangement, we didn't have the isometrics Naja. In the beginning of the project, we didn't have the isometrics because normally we are delivering the piping science to the piping engineers. By the hydraulic calculation we did. But to do the hydraulic calculation, we need to know the full length, the full distance the fluid or the pipe will flow and will move between one equipment to another. So based on that, we didn't start our calculation until the piping engineer or the layout engineer finish the layout of the plant by saying that we will put this equipment on the right, we will make a big pipe rack, we will put other unit on the left, and this unit with the compressor will be here downwind. All this configuration. Let me share the layout of the plant we are speaking about to understand what I am saying. Have a different lot of layouts. So layout. Can anyone help me? No one is helping. Hello guys. Can anyone help to support me? You have all the transmitter. I am searching for all the transmitter for the layout. I didn't find it. Okay, let's draw it. Here is the white screen. Here is what we have on site, what was proposed from the engineers. Here is on the far side. What I am drawing is typically what we have there. Here is the big manifold, and here is underground pipelines all the way to the tie-in point for our plant. Then we have a big pipe rack. Then we have the descender here. The gas from the descender, or the stream from the descender, go to the three-phase separator, where we have the gas, the liquid here and there. This gas is going back like this way to the compressor, and the liquid here condensate is going to the surge drum, or it's going to the pumps. It's going out. The gas is coming here, taking all this. You join with the liquid, then send it back to the boundary limit. And the water is going to the evaporation pond, which is outside the plant. The same for the water from the descender. Descender, 3-phase, separator, compressor, surge drum. The reason, Naja, why I am drawing this is, as long as on the beginning of any project, any detailed engineering, one of the deliverables we need from the process department is the hydraulic calculations. Basically, ammonia. When process team making the hydraulic calculation, they did the hydraulic calculation on the longest way. The question is, when we make the pipeline isometrics, as I make it like this, here is the piping isometrics. We didn't receive this one until the piping discipline finalized the general arrangement at the end of the project, until he finished the 3D model. So, how we can, as a process engineer, finalize our hydraulic calculation and make sure that our hydraulic calculation is correct at the beginning of the project. We take the general arrangement from the piping. General arrangement from the piping is normally like 90% didn't change in all the phases of the project. So as the piping makes this a layout, we will not change it by percentage of 90%. So based on that, what we are doing is like we want to make the calculation from this wellhead. We want to make the calculation for this pipeline. From the piping, we take the full length and number of fittings, elbows, valves. All this is under the word fitting. We take this and we multiply it by 1.3. Based on that, we make the hydraulic calculation. For every one of you, it is not clear. Let's make a practical example to make it easier for everyone. Okay? Okay? Who is waiting in the lobby? Naja is away. Mark, can you enter Naja, please? Mark. Hello, Mark. Can you enter Naja? One minute, I will text Mark. as it were to. Can you join me? Yes. Need your help. Mark, can you enter Naja? Mark. Sorry for this, but Naja was signed out from the two accounts. I just don't want him to lose this spot. Okay, Mark is back. What's this? Naja. No, he's in. Naja. Naja. Don't worry, I don't like to look to the chat page. I was always focusing on what I'm presenting. So if anyone have any problem with this, just text me as you did, Naja. Okay? What we was saying that, let me show it again, just you can keep up with us. You see this one, Naja? It is the general arrangement for the piping. Who was proposing the layout for the equipment, for the pipe rack, for the flare stack. This general arrangement is 90% fixed. We can fix it at the beginning of the project, at the beginning of the detail engineering. If we are decided to wait until we get all the isometrics from the piping, we will not be able to finish the hydraulic, because we need to know the size of each one. We need to know the length of this piping. We want to know the number of fittings, which will be the elbow and bolts. If we know all this, we can make the hydraulic. Without this, we cannot make the hydraulic. So, and based on that, what we are doing is that, for example, we are going to make the pipeline between the descender and the separator. This pipeline, if we decide to make this pipeline, we will ask the piping what is the different distance between the descender and the separator, what is the full length, proposed full length, what is the number of fitting elbows and valves. Then we multiply it is by 1.2, 1.3, depend on whatever conformity level you feel with your piping engineer. For me, I always multiply it by 1.3. Then from this one we can jump now to the ISIS. Which line we decided to do is this line, for example. Let's take this one. The condensate to surge drum. We want to know how to size the condensate to surge drum vessel. So what I will do is F4 to make the new streams. Here is another stream. I will define it from another stream. I will take copy or paste from this stream. Copy paste in HYSYS is not such good tools to use, so I will need to take it defined from other stream. Condensate to surge drum. I will use condensate to surge drum. Here I will take the temperature, the pressure, the flow, the composition, the coloration, everything. Then I will say OK. So we have now a stream equal to this one, the same stream, everything. Here is the temperature 47, 16, 56. Here is 47, 16, 56. Then I will introduce a pipe segment or a gas segment. Pipe segment, it is used for gases and liquid together or liquid alone. In this case we are using liquid alone, condensate surge drum. We'll send some liquid to the surge drum from the separator. Then here's the piping. What is entering? Number 1. What will be the outlet? Will be 2, for example. Energy Q3. Then he will ask for no sigma added. We will go for parameters, for rating, sizing. We will add segment. Everyone can see this. Everyone can see this. Focus, please. Please focus. Basically, we are dividing our pipeline into subunits. For example, if we have a pipe, let's start from the beginning. 180 degree closed return. We have an angle valve 45. We have a pipe 90. We have ball valve. We have a pin with a radius diameter 20, 30, 4. We have a butterfly valve. We have a check valve. We have a diaphragm valve. We have an elbow. We have a gate valve. We have a plug valve, and keep going. So let's start with this one. Assuming that the liquid from the three-phase separator is going all this pipeline till the surge drum. When we ask the piping engineer, he tell us that this pipe segment is almost 20 meters between the three-phase separator and the surge drum. Is there any elevation change? Is there any elevation change? Does the nozzle of the separator will be on the same level of the nozzle of the surge drum? No, there will be 0.5 change. Is it positive or negative? Mean it's coming from high to bottom or from bottom to high? If it is coming from high to bottom, it will be positive. If it is coming from bottom to high, it will be negative. So 0.5 is good. Now let's assume a diameter. Double click here. Then you will have this one. What is this pipe segment? Here is all the standards for the piping. Schedule 10, 20, 30, 40, standard schedule, 60, 80, 100, double XS and 5S. Every piping schedule, all the ASME schedule piping is here. So what's typically we're using is schedule 40. Is it all? No, we didn't mention the diameter till the moment. Here we are, starting for 8 millimeter, which is equal to half inch, till 100 millimeter, which is equal 4 inches pipeline, 200 meter, 8 inches, and keep going till 900 millimeter, which is almost 72 inches, something like this. Now, how much is the quantity we are speaking about? I don't know. So 1, which is the entering to the pipe segment, which is the outlet of the 3-phase separator, normally have like 56 kilogram mole per hour, which is equal to 6.7 cubic meter per hour. 6.7 cubic meter per hour. Let's assume it is 4 inch and see what will be the velocity. Take care, Muhammad. Now I am trying to try and error. Try and error of what? I am trying to propose radius, then check the delta B and velocity. If it is within the limitation, it is okay. If it is not within the limitation, I will reassume another piping, maybe increasing the pipe diameter, maybe reducing, depend on the results. Okay, Muhammad. Okay, double click using scheduler 40, then we will go for the 4 inch 100 millimeter. Automatically he nominal diameter, I input 400 millimeter, he bring from the ASME P31.3 the inner diameter. The material we have, which is carbon steel or mild steel. If we have for firefighting, we can use the plastic tubing, which is the PV, polyvinyl chloride PV materials, or we can use a smooth concrete if we are going to make a water treatment plant, or galvanized iron or cast iron, depend on which type of metal you are pumping your liquid. Then automatically bring the roughness, automatically he bring the wall conductivity, the thermal conductivity, to calculate the pressure, the temperature drop in the pipeline. Then we close it. You'll find that this is what we enter: 20 meter pipe lengths, elevation 0.5, change from high to top, from high to low, from top to bottom. And here is the 4 inch pipeline. The material is mild steel, the roughness is already there, the conductivity is there. We have all of this as input. Muhammad, we have a problem. Naja, we have a problem. What is the problem? When we ask the piping engineer, he tells us it is a 20 meter. But it is a rough estimation from his side, because till the moment we didn't know the root of the piping. The root of the piping. We didn't know the isometric of the piping. So, based on that, we will assume this 20 meter, we multiply it by 1.2 to be 24 meter. You got my point? We will check this one, but let me finish all the input from the piping, then we will check the velocity, then we will check everything. Exactly. Is that all for the piping? No. The instrumentation department will install a control valve for controlling the liquid inside the separator. This control valve will make a pressure drop across the pipeline. Is that all? No. Let me share the print again so you can see what I will draw. Normally, when we have a separator here, then we have a piping with a surge drum. Normally, we will have a control valve taking the signal from this separator. Is that all? No. We will have also a manual valve up and downstream of the control valve. This is a level control valve. This is a manual valve. This is a manual valve. Also, we will have a bypass for this one with two valves, one globe and one pole. 20 meter, we take it from the piping, is this. Let me choose another color. Simply this pipeline length is 20 meter. What else? We need the delta B for this control valve. We need the delta B for this manual valve. We need the delta B for this manual valve. What's the type of this valve? It is a globe valve. Is it also globe valve? So, and this one is globe valve. This is a manual, this is a controlling, automatic. So, let's go back to the HYSYS. What we have a globe valve. Let's search for a globe valve, globe valve, globe valve. Where is the globe valve? Okay, slide, check, and go. Here we are. The globe valve. Globe valve. Is it will be open? Yes. Is it will be half open? No. Is it will be crack open? No. It will be open. The size of the globe valve will be the same size as the pipeline. Here we assume the pipeline is 4 inch, so we will insert here 4 inches. How many globe valves are there from what we draw? We have 2 globe valve, right? Then we have another globe valve. This one will be half open. This one for the controlling. This is the level control valve. This is the manual valves, up and down the control valve. It is the same size, 4 inch, but this is a one control valve. Now we inserting all the pipe lengths and the fittings and valves on the piping. Anyone have a problem? The layout of the area of the plant. That's the area of the plant decide what we are going to do. Are we going to have a much space between equipment, or we will have like congested area? It is depend on the available area. If you go for, can you make a mute? Because I'm listening to my voice. I will answer this. If we go for offshore, typically the spacing between equipment will be almost nothing. 1 meter, 2 meter maximum. The spacing between equipment and each other. On the onshore facilities, typically the spacing between the equipment maybe reach 100 meter, no problem. How we can make this, how we can do this, it depends on the available layout from the client. Normally, if I am going to make a new plant for my company, the first thing I will make the space for it. In my case, my company and my gas wells is coming to be inside the farmer area, farmer land. So I will rent this land from the farmers first, then I make sure that this layout is more than enough for the processing facility and for the utility and for the accommodation. Then I will make the available for the space area from the whole areas, and I give it to the engineering company. Then the layout engineering will make the white board and make this best utilization of this area according to what we are drawing. Here is the main pipeline, here is the main piping rack. On the right we will put the separator, on the left we will put the compressor, to make sure that we have the minimum piping length. Is that all? No. Because on the other side, if he have a bad layout, he will end up by having a lot of crossing and a lot of useless amount of piping. For example, if he put the compressor on the same side of the separator, in our case, this means the gas line will flow for a small quantity or a small distance till it reaches the compressor, like 10 meters. But if he put the compressor on the other side of the pipe rack, this means the gas will flow more than 40 meters. 40 meters of piping, of 12-inch piping, which will cost you a lot of money. So EPC contractors normally, the first thing they are trying to minimize is the cost of the piping. How they are going to do this? If they have a good layout, they will try to shorten the distance between the equipment. Is that fair for you as a client? Yes, it does the purpose, but on the other hand, it is not good. Why? Because making the distance shorter between the equipment make it harder for the accessibility and rentability in the future. So in the 3D model and on the arrangement of the plant, you have to consider the availability, the rentability of the equipment. And Naja, you are your background is the safety, right? I remember, right? your background is the safety, right? Yes or no? No, your background. Your background is HEC instructor, right? Not you. Ah, okay, perfect. This means from your side as an operation, if you have the accessibility of the equipment is not available, you cannot reach this valve. You have to make a ladder for this vent. You have to make a platform this valve. It will be very hard life for them. What we are trying to do as EPC contractor is to minimize the piping as much as we can, because minimizing the pipe means a lot of profit for us. On the other hand, you as the owner, you have to make sure that the operator will be comfortable during his activity. There will not be a lot of trip and slip hazards. Thus you can check on the 3D model, and 3D model is the output of the general arrangement which we are speaking about, Muhammad. This is the full cycle we are speaking of. General arrangement, making the maximum piping, maximum utilization of the area we have, not making a congested area. Then when we have this, it will be more than fair that you have a lot of spacing between the equipment, so your operator can work easily, safely, and you have the availability and the maintainability of the equipment. You got my point or not? Totally right. Still one point, Muhammad. Is there still one point I want to add? After making this, the general arrangement, the piping will propose one, and the process safety department in the EPC company will ask for a minimum distance between equipment. If you work in a big company like wood, the process safety department will have a lot of input to the layout. If you work in a small companies like Excitran, like Qualiperson, you will not find this input. Why I'm saying this? Because if you have a good spacing between the equipment at the beginning, you will make a lot of hydraulic calculations in the correct way, and you will not redo the work again. On the other side, if you don't have good spacing, you will end up by small amount of piping. You will end up by hydraulic, which you will make it correct, by the way, but you will do it again when the process safety fire risk assessment study output will be done, and will ask you to make this separator far from this equipment, far from this heater, far from this, and basically you will redo your hydraulic calculation again. So for big companies like Wood, what they are doing, anyone know something about process safety? Let me ask Naja on another word. Naja, do you have a heater in your plant? Where is the location of this heater from the nearest equipment? What is the distance? $55.0, right? This 45 meter is the minimum in the CCPS, Central Processing Safety Institute in UK, which give a minimum distance between equipment and each equipment and the other. It mentioned, Muhammad, take care of Muhammad about this. The heaters must be in a distance about 45 meters between the heater and any process facility beside it. Tanks must be almost 15 meters from each other. Tank, if you have a tank and another tank, the minimum is 15 meters. You cannot get a tank close to another tank less than 15 meters, 15 meters, and keep going. If you respect this layout at the beginning of your project, you will end up by having a layout at what's called comfortable layout. So you have a good arrangement, you respect the process safety, you will end up by have minimum impact on hydraulics. Then you will do your hydraulic one time. You got my point, Muhammad? Okay, now we have input for the pipelines. We have the flow valve, we have the control valve. The HYSYS asked for heat transfer information under specified. Then if we go to the heat transfer tab, we're going to estimate the heat transfer coefficient. It will ask you from the ambient temperature, is this piping underground or it is above ground, in the sea, or what? Normally this piping between the separator and surge drum, it will be above ground, 50 meters above ground, 50 centimeters above ground. So it will be, ambient temperature will be the same as the normal air temperature. So 35 will be more than enough. Then include pipe wall. Yes, please. What's the pipe wall? Here, let's go back for the sizing. Do you remember this one? Wall conductivity. As you see, it is almost 26 BTU per hour feet Fahrenheit. It is the amount of energy can be transferred inside the wall, the pipeline thickness. Inside the pipeline thickness is 45. So when we go to estimate, we just simply, please, when you're making new calculation, make the pipe wall. If this pipe wall is insulated, we added insulation. If it is underground, we added the type of the, is it air, water, or ground? And even we specify the ground, if it is wet or dry. This is not our case here. This is a normal piping on the ground. Then here's the sizing. We make it everything, and it is green. Let's close it. Now it is calculating. Let's show table here and show table here. Okay. The delta B is almost nothing. It's entered by 16.22, it's outlet by 16.19, which is nothing. But the temperature, we have a good impact of the temperature because of the ambient temperature. So it is coming 35 Celsius instead of 47. The question is, the white screen of the HYSYS. Is clear now? Can you see it now? Here is one, here is two. When we solve the pipe segment, it is entered. It was entered by 16.22 bar sheet. Its outlet was like 16.19. Is it good or bad? The differential pressure is nothing. in 20 meters or 24 meters. So from pressure perspective, if we're going back to total standard, which mentions that we want, let me open total standard again to make sure that we're following it one, this one. Total simply mentions that on a normal process pipeline, the delta B will be 1 bar maximum per kilometer, and normally will be 0.6. You got my point, everyone? 1 bar maximum per kilometer. So back here, this almost 0.03 bar G for 24 meters. Let's calculate it. Calculator here. 24 meter. Let's write it down. Why am I making this one? Share my screen so you can rejoin me. What we are saying is that we have delta B equal 0.03 bar for a length equal 24 meter, right? That's what we get from the ICES. The total specs mentions that 1 bar for 1000 meter. So 0.001 for every meter. We have here 0.03 divided by 24 to get how much delta B per meter. So utilizing my calculator on the desktop, 0.03 divided by 24, this means we have here 0.000125, which is less than total standard. So from total perspective, it is ready to go. It is acceptable for the delta B. What we need to calculate is also the velocity. From total perspective, we say that this line is 4 inch, so we need 1 meter per second is our maximum. 1 meter per second is our maximum for a 4-inch pipeline. So instead of making the calculation like this one, I will jump back to the HYSYS and ask the HYSYS what is the velocity. You see my screen, right? HYSYS screen. Low. Okay, let's see. Thank you for saying this, because without this I cannot. No. Did you see my screen, the HYSYS screen? Okay. We will ask for the performance and the flow assurance. What's the flow assurance? If we have, this is one of the capabilities of HYSYS, CO2 collusion and erosion velocity. Erosion velocity, what we are seeing from the API 14E. ask to a calculation in velocity. Scale. Here we are. The length, the density of the fluid, and the velocity for our fluids in meter per second. What we was accepting from total standard was 1 meter per second. What we are having here for 24 meter length pipeline, we will have the 0.238 meter per second across all the pipeline until it reached by 0.236 at the end of the 24 meter. You got my point? So, exactly. What? Why what? What's density? I don't get it. Yes? Because of the temperature. You have the ambient temperature 35. I was entering by 47, so the pipeline will be hot, will be losing heat to the atmosphere. That's what. Yes. Tell me what you are not understand. The temperature decrease, so the density increase. And take care, it is increasing by slightly nothing. Yes, tell me. Yes. Do you love wood? The wood. Did you work as a carpenter before? Do you have any house activity like a husband and please make this surface, make it smooth? What are you doing when you want this wood surface to be smooth? No, it is not clean. You bring like what is the meaning of samphara in English? Let me ask for the meaning of. Let me ask Google for the meaning of one of the Arabic words. Do you know sandblasting? What's doing sandblasting? Huh. We're using the sand particles with the high pressure of the air to make like plastic, to blast all the surface, right? It is the same original velocity. We are afraid from the fluid velocity, fluid high velocity, which in this case, if it is liquid, will be 10 meters per second, which is if it is a gas, will be 30 feet per second. we are upgrading from this high velocity to making the same impact of sandblasting inside the piping. That's why we are trying to avoid working closing to the original velocity. That's why we are trying to avoid working from such original velocity. Because if we working to such a original velocity, there will be like a sand blasting effect inside the piping. And if this pipeline is decided to live for 15 years, it will have a big hole after 1 year. You got my point? In this case, HYSYS didn't calculate it because you are very far from the original velocity. Let's calculate it. If, for example, here we ask that the pipeline was 24 meter. What happened if instead of outer diameter 4 inch, we decide to make it like 2 inch? Let's try 2 inch. You are seeing what I'm doing? It's still calculating. Then we have the performance. Then we have the flow assurance. Did you see the velocity? What happened to the velocity? That is jump, right? You didn't reach the original velocity. Let me continuous. Very defined. You are very far from the original velocity, which is good. I don't know why. Why we are making this? Let's calculate it from by manual. API 14E, and let's share the screen with API 14E and calculate it manually. Let's bring the equation. This is the sizing for the original velocity for the two phase. I'm searching for one phase. I don't understand what you say. Say it again. I don't understand what you say, wallahi. Sorry. I was focusing on the equation, trying to bring what for the single phase, but I didn't see it for the single phase. It was only up here on the gas, because this was an old edition. This is the equations, the general pressure drop calculations, not my interest. Let's assume it is this one. Here is the C constants will be 100 for continuous surfaces, 100. Let me let's assume it is 100 multiplied by gas liquid density by Libras by feet. So I will switch to HYSYS just to bring the density. Density 0.49. This would be your equation. So you can divide it and tell me what's the number. Hello, Muhammad. Can you divide it? Help Naja in calculating this. Tell me the number. Mark, please, can you make phase enter again? Mark. What is the number? Sorry, Naja, I don't follow this. I was trying to make him enter 142. Right? It's too far. It is too far from what we have. We are less than 1. So that's why HYSYS was not going to present it. Out. Phase is out. Sorry for this, I'm trying to make phase entering. Done. Faiz, welcome back. Don't worry, we have all this lectures is recorded and we will share it after this. Don't worry. You got my point, Naja? Sharing back the HYSYS, here what we have. So he didn't calculate the 142 compared to the 0.9. That's how we can make hydraulic calculation simply and basics for HYSYS. Now let's make the idea of making hydraulic calculation and how we can do it. What we are trying to do is, you see my presentation, right? Hi everyone, you see my presentation? Okay. Till the moment we do the hydraulic with HYSYS, then we will have the presentation, then we will do it with Excel sheet of Wally Parson, then we will take our assignment for the D&IDs which I shared with you yesterday. Okay? Before we take the assignment, we will discuss the P&ID you dropped me yesterday. Okay, anyone listening? Okay, as you can understand from what we just did on HYSYS hydraulic, is simply we want to transfer a fluid at a certain rate from a source to a destination. Whatever is a fluid, is it liquid, vapor, or mixed phase, whatever the rate, is it minimum, normal, or maximum. How we can do this? Ensure capacity by allowing for varying conditions, changes in sources, destination pressure, elevations, flow paths, or density. We can do hydraulic. We can make sure the hydraulic, if we know the pressure, the elevations, the length and the path of the fluid, we know the viscosity and the density of the fluid. What a hydraulic system is composed of? What is the input for a hydraulic system? Source. As you see, we take it from the three-phase separator. Line. We take it from the piping engineer. Did we take isometrics? No, we didn't take isometrics. We take a rough estimation. That's what we have on the beginning. That's what we have on the beginning to make sure that we are producing the hydraulic. Then, after the complete 3D model, and we have isometrics, full isometrics, and be concentrating on this full isometrics, we recheck our hydraulic calculation again. Then, if we have a pump or compressor, then we have the line optionals, if we have any branches, if we have accessories on the pipeline like control valve, or then we have the destination, the end point of the fluid. Source, then we have a line moving to pump compressor, then we have a line moving to control valve, then we have a line moving to a destination. This and this and this three representing the total length. Anyone didn't understand anything, just stop me, okay? Yes. What is the what? Yes, exactly. No basis. Yes, there is no standard for it. Basically, the pressure drop, you can accept whatever pressure drop you want. On other word, Muhammad, if we have a pump here and we have a pipeline here, if this pipeline is, if the size was small, we will have a pressure drop very high, right? Right. Some companies like BB will ask to increase the size of this pipeline. Some companies like Shell will ask to increase the power of this pipeline. Increasing the power will overcome the differential pressure and make the flow reach the destination. That's what we are trying to do. By the end of the day, hydraulic is to make sure that fluid moving from this point reaching this point. That's what we are trying to do. Delta B high have impact to using a high power here in the pump. Some companies like Shell accepted this word. Some company like BP didn't accept this word. They're trying to make the delta B as minimum as they can. So to reduce the impact on this pump and make sure this pump long lifetime. You got my point? When you work in engineering firm, this delta B can reach to 1 bar by 100 millimeter. If you're working in EPC company, because this one is not right. When I say it is not right, I mean it is not a common practice. What is the common practice? 0.1 bar every 150 meter. This is what you can see in ADNOC specification, Aramco specification, Oman specification. That is copy best. In Qatar Gas it is 0.05. You got my point? Okay. Here we are. The source is the destination, the flow. Pressure source must be higher than pressure destination, so flow can go this way. If we're speaking about liquid height here must be higher than liquid height here, so the liquid can flow. Pressure plus liquid height, if we have two mixtures, must be higher than pressure and height in this way. If we want the liquid to flow this way, we have to make sure that this pressure is high enough to push all the liquid to overcome this liquid height plus the pressure here. The same here. Pressure plus height liquid here must be lower than the pressure of height liquid at the destination, because we use a pump. I don't get it. Here this was high, so it's moved by natural. Here was low, so I use a pump. Required information for a hydraulic system: PFD, B&ID, material balance, to know which material and to get the physical properties, the density, viscosity, and all of this. Operation cases, as we mentioned, we have 3 cases. Plant pressure profile defined on the cases: 250, 500 plus 900. Equipment dimension and elevation, as you mentioned before, as you said before. This equipment is higher than this elevation, this have to be implemented during the hydraulic. If it's 0.5 height, if it is negative, depend on the way of the flow. If it is moving like this, or it is moving like this. Like this will be 0.5 negative, like this will be 0.5 positive. Design instruction and design factors, or in another word, limitations. And plot plan, plot plan, Muhammad. Naja, you got this one? Okay. Anyone want to say something? Anyone don't understand something? Anything? Okay. This is the way we are used to do in Wally Person and CPI Limits also the same way. Documentation in hydraulic sketch. In EPC company, we have the juniors, process engineer, we have the senior, we have the chief. Junior to transport the information, transfer the information to the senior, and from the senior to the chief. We have to have the hydraulic sketch, which demonstrate, which show the source and the installation pressure as a fixed reference point. We have a pressure of 250, for example. Source will be 3-phase equator. Destination will be slug, surge, drum. Flow bus, length of the piping, accessories of the pipe, equipment elevation and dimension. This equipment is higher than this by a distance. Liquid level, if here we have a liquid level and here we have a liquid level. What's the difference between them? What is the difference between the normal operating levels? Equipment pressure drop. We have pressure drop on the equipment here, yes or no? Flow meter and the pressure drop. We have a flow meter on the pipeline and the delta B, which is make, if it is orifice flow meter or venturi flow meter, and how much delta B is make. Indicate clean, fouling, SOR or EOR. Fouling is what happened inside the heat exchangers. We have the fouling effect, which increase the differential pressure in the pipeline. Control valve location, elevation, and node point, the final point. You got my point? Okay. Here is the points we need to identify. Point 1, 2, 3, 4, 5, 6. Here is the point we need to identify for such system. What is this system? Enter here and enter here. Here is coming through a valve. We need to know the pressure here. Then we have air cooler, which have a delta B of 1 bar. Then we need to know the pressure here. Then go all this way, mixing with what's coming from this side with flow indication, which have delta B 0.25 bar G. Then we have a control valve. Then we have going to the cooler 0.05 till it reaches the final destination. What is this? It is a system coming have 2 in mixing before we have 1 outlet. Hydraulic perspective, we're making this hydraulic alone. We're making this hydraulic alone. And then we're making hydraulic from this section. This is the hardest hydraulic system you can ever see. This is the hardest hydraulic system you can ever see. Okay. Line sizing tool. Have the maximum flow rates, which is the worst case. Always remember this. Worst case is what we import. Fluid phase, operating temperature, densities and viscosities. Line sizing criteria should be taken from our client as a Total or PP or Aramco, whatever that we want. Equivalent lengths which we taken from the piping. Pressure drop limitations. Select them. You can select the line. As you see from the previous example on HYSYS. If we selecting 2-inch pipeline, or we selecting a 4-inch pipeline, or even we go for a 6-inch pipeline, or even 1-inch pipeline. If we are working close to the limitation, please jump to the next size. The previous example we did on HYSYS, if we start with 2-inch and we find the velocity is almost 0.9 meter per second, and where our limitation is 1 meter per second, we have then to jump to the next size, which will be 4-inch. Why 4-inch? There is a 3-inch pipeline. Why you are not using the 3-inch pipeline? You can use it, but because of the 3-inch pipeline is not always on the shelf for the suppliers, we always jump for 2, 4, 6, 8, 10, which will be the on shelf for the suppliers. But even numbers like 3, 5, 7 inches, you will be asked to be like a special order for you, and it will cost you a lot of money. So in EBC or even in owner, we jump the 2, 4, 6, 8 inches. We didn't go for the 3, 5, 7 inches. Okay, for a pump, compressor, hydraulic sizing, we need to define the same as previous. Sources is a fixed for every part, flow rate and operating condition, prorated rates or conditions. This is important for the pumps and the compressors. Equipment elevation, pressure drop, flow meters, pressure pump head also is important, and control valve DB is also important. What does this mean? Prorated rates conditions. What they asking for is that this compressor pump, how much power I will need for the pump or for the compressor to compress liquid or gas. So from the line sizing, we can, from the rating of the pump, from the rating of the pump or the compressor, we can understand or know the value of the pressure outlet of the compressor or of the pump. The power here will help us to know the discharge pressure, and from the discharge pressure will be the source for the pipeline, and we can do the calculation. Is this all? No. The power can be represented in pump head. Normally, Naja, when you contact a vendor, he told you My pump head is 100 meter, 80 meter. That's correspond to 8 bar. This correspond to 10 bar. This means if the pump here is enter with 1 bar as a section pressure, 1 bar, the outlet, if it is 8 bar, it will be 1 plus 8, it will be 9 bar G. You get my point, Naja? Head of the pump, then we ended up by 9 bar. That's why sometimes during operation, if the 9 bar is not achieved, you check the section and maybe you find one of the valve is partially closed. That's important to know the 9 bar, just to make sure that this 9 bar will be used for the hydraulic. Okay. Why we are making hydraulic? It is the best and most efficient way of transporting a fluid. We need to be a reliability. We need to make sure that our pipeline have a good reliability, safety factors, fluid behavior, and upset and variable condition. We need to make the OPEX, operational cost minimum, power consumption minimum, pressure profiles maximum. We need to make the CAPEX, cost of the material minimum, cost of installation also minimum. That we are trying to make for a line sizing. Okay. Muhammad, can you read this part please for me? Muhammad, can you read this part for me please? Simply, if we choose the wrong size for the pipe discharge, did you see any pump vibrating before, Naja? Why? Did you face any piping, any pump which is failed during the startup and the commission? I faced it in my project owners. We have one of the pumps. The line sizing was not right, which make a lot of very high velocity, which impact on the noise, high noise, and impact on vibration. That ended up by pump damage. The good part that the guarantee from the vendor was still valid, and the vendor replaced the pump and the pipeline on his cost. So, line sizing is most critical. How we can make a line sizing? Collect info, define objective and criteria, generate options, simulation, evaluation, select, improve, report. Which I Dorsor. I for info, D for define, options, simulation, evaluation, selection, improve, and report. This is what we just take in when we make for the HYSYS. We take the information, we define the screens, we set the criteria from total. We didn't make any options, it's only one option because we are in a training. Then we simulate all of this. Then we evaluate, seeing the fluid velocity, see how much velocity we have. Then after that, when we see the velocity, then we select the pipe size on the 4-inch. See, it is good, okay, keep it. It is bad, no, switch from it. See 2-inch and see 6-inch. Then improving, we will keep the 4-inch, it is a good velocity. Then reporting that this pipeline was sized in a 4-inch with current fluid velocity like x.235, which we get it from the HYSYS, and we are on the safe side. We will keep this pipeline in a 4-inch. You got it, Naja? Muhammad? Perfect. Faiz, I miss your voice. What's yes? Yes, you got it, or yes, you didn't get it? Okay. Perfect. Okay. This is the equation in the behind scene of the HYSYS, or in the behind scene of the Excel sheet, which I will share it with you. Let me share the Excel sheet with you now before we close, because I want you to use it. Okay. Can everyone open his WhatsApp? So we will share the calculations. Then we will have. I was going to send it to Mark. Design. And these two calculations, you will find hydraulic calculation for liquid, hydraulic calculation for vapor lines that we are trying to do. Let's go back to the presentation. Average velocity is a function of the area multiplied by the root of the 2g by the delta p. This means the delta p is in relationship with the quantity of the gas, or the quantity of the liquid, as we said, to the power of 2. Okay. Essential relation for line sizing: friction losses caused by drag, caused by friction between two surfaces in contact that are moving relative to each other, which is the viscosity, flow regimes, roughness of pipe, result in a pressure drop added in factors, which is F with this equation. Before we have here the H is the output of this equation multiplied by the F factor for the frictional losses. Flow regime, we can have a laminar flow like this, which have a velocity little bit slow, or turbine flow, which we have turbulence, and this can be judged by the Reynolds number. For a laminar flow, it will be less than 2320, and for turbulent flow it will be more than 2320. As you know, everyone, laminar Reynolds number can be calculated by the velocity, density, and line diameter, and the viscosity of the fluid. What is the essential relation for equations? Darcy is the most critical for us. Darcy equations is the most common and everyone use it. Delta B is multiplied of average height of all the perforation in pipe, the height of the vessel multiplied by L, which is the length of the pipe, divided by D, which is the diameter of the average velocity, average flow velocity, multiplied by 1/2, multiplied by P, which is the where is P? Pipe selections. P is the density of, it is not P, it is rho, the density of the fluid, and the average velocity of the fluid. That's what we are trying to do. That we are trying to calculate. The delta B, which was 0.02 in the previous exercise in HYSYS, was calculating on Darcy equation like this one. There is another equation called Hagen equation. Hagen equation, he ignores the velocity because the Reynolds number already has the velocity from the previous equations. The V on the upper side. Color probe and white coloration for turbulent flow. Some customers ask for it, like Aramco, because it is how I can say, a coloration to the power of -5 accuracy when you're using color probe and white coloration for turbulent flow. But normally Darcy is satisfying your needs for every turbulent flow. Hagen for every laminar flow satisfy your needs. Color probe sometimes depend on the customer how accuracy he want for the line sizing. Anyhow, Moody versus fanning. Fanning friction factor is 1/4 of the Moody friction factor, so attention must be paid to know that which one of these is meant in the friction factor chart or equation consultant or equation consultant. One of the two, fanning, is the more commonly used for chemical engineer and used following British conviction. Because when we're working with CB&I Lummus, which is American company, compared with ABB, which is British company, most British use the Moody factor, Moody chart, and they using the Moody constants. If for the fanning is using in the American constants. By the end of the day, HYSYS using the Moody friction factor. Here is the charts which we are searching for. It's making zoom inside of it for it. Here is the laminar flow. Here is the critical flow. Here is the turbulent flow. Here is Reynolds number. Here is the fraction factors, which is the Moody one, not the other phone factors. Here is the relative roughness K/D for the pipeline. equivalent length. Let me see what it's or something. Equivalent length is what we are searching, what we are trying to calculate in the Excel sheets when we saying that there is 5 manual valves on the pipeline or 6 control valve on the way. Let me say it in another word here. If here is the pipeline, if the length of the pipeline was like 1 kilometer, if we have a control valve, if we have the manual valves here and there, the equivalent length will be 1000 meter plus the delta B of this control valve equal to the delta B of 10 meter piping. So we'll add for this 1000 10 meter. The delta B for this manual valve is equal to 5 meter piping. So we'll add extra 2 5's because we have 2 control valves. So the equivalent length will be the total of all of this, which will be 1020 meter. This depends on the accessories on the valve, the elbows, the whatever we have from the isometrics. Okay. Equivalent verticals. Okay. Let's from here. Let's write it here, which will be easier. Simply, as we mentioned before, there's the piping isometers like this one. Control valve here, and manual valve here, and the control valve here. The total length will be, if we start from here, end it here. The length of the piping is this one. Assume 5, 2, 2, 1, 3, 2 meters, 1 meter, 2 meters, 1 meters, 1 meters, 2 meters, 1 meters, 2 meters, 3 meters, 4 meters. Make it 5 to make consistency on the road. Total length will equal to the same way we are entering the piping isometry inside the ICES will be 5 meters, which is this 5, minus 2 plus 2 minus because we are going down, 2 positive we are because we are not going up or down, we are still on the same. This I'm a bad drawer. It's like this one. Then we going up another 1, then we move 3 here, then we go up, then we make 1, then we make minus 2, then we make plus 1, plus 1, plus 2, minus 1, plus 2, plus 3, plus 5. All this pipe actual lengths plus the delta B here, delta B here, delta B here, which will be on a minus 20 as the same we calculated before. Is equal to 5, is equal to 10, is equal to 5. This will be the total length of the piping we have here. Let me extract one of the isometrics from my old drawings. Naja. Naja. Did you see isometrics before? Sorry? Yes. Why you didn't say anything? What you seeing now? Yes. Faiz. Faiz, yeah, Faiz. Is it black now? Suppose now you are seeing my isometry, right? Alhamdulillah. Okay, Muhammad, you seeing it? Muhammad, Faiz. Okay, Faiz, you see it? Okay, Muhammad. Muhammad. Perfect. Let's see. Here we have the inlet. Let me draw to make it easier for you to follow. Okay, here was the vessel, and here is the first tie-in, first valve on the outlet of the vessel. Then the pipeline is moving this way. Then we have an angle here. Then it's moving this way. Then we have another 90 angle, like this, another angle. Then like this. Then going down. Then moving underground for 200 or 200 almost 5 meters, sorry, or 5 meters. Then going up again for almost 1.6 meter. This kind of the isometrics we receive from the piping. Then let's continue on sheet 2. Let's go for sheet 2 just to make you familiar with the isometrics. Here from sheet 1, keeping the same way. Now continue on sheet 3. Here we are, down, up, down, up, down, up, all the accessories on it. Back to the first page. The good part about the AutoCAD or the BDMS software which is using by the piping, that and give you a complete material takeoff MTQ. He mentioned that you have on this sheet 8-inch pipeline with a total length 19.9. We have 2-inch pipeline with a 0.1 meter. Then we have number of elbows 8, size 8. We have 1 elbow 90 degree, we have 7 elbows. For elbow 45 we have 1 elbow, both are 8 inches. Then Then we have a valve. We have a ball valve, 8-inch, one control valve. We have a ball valve, 2-inch, one part. From here, you can extract the inputs to the. Let me share the hyces again. Which we want input here. Do you remember? Here is the pipe. Here is the global valve. Here is the ball valve. Let's input, for example, elbow 90 degrees standard, which is the same 2-inch. Number of the valves 7. You got my point, Naja? You got my point, Muhammad, Faiz? And based on that we can see the flow assurance, and we can have the flow and the velocity. You see the velocity increase at the bottom because we are identify the elbows at the end. Here we are for the piping. Here we are for the whole system. Now I have a problem, Naja, sorry. I have a problem. What the problem is, I didn't know the pipe length for this one. I didn't know the pipe length for this one, and this one, and this one, and this one. So, Muhammad, focus please, because this will be your homework. Muhammad, write after me, please. The same for you, Faiz. Okay. Let me share the process flow diagram. The first task will be writing after me, please. Make this simulation the same as I did. Everyone write after me. Everyone write after me. I need a confirmation from everyone. Everyone, not Muhammad only. Is this a confirmation, Naja? Okay. Then, after this, we will have the simulation. We will make the hydraulic for your pipeline on hyces. Like this, what I did. This will be completely recorded and will send to you for the link. Don't worry. Then, let me share the PDF. This one. Here is what we have for Total. For the limitation. From the process simulation, you will have your process input. You will have the pressure, the temperature, the composition, the viscosity, the density, whatever you want. And here is your limitations. Here is your what? Limitations. I appreciate if anyone look to the other standard, say asking for other limitation. If you can check Foster Wheeler, ABB, ExxonMobil, Shell, whatever, Sahara, if you are working, Muhammad, who you working, Aramco or Sabic? Which company you working for? Muhammad. What's your company? Yes. Excellent. Okay. Perfect. what I want for you is tell me what's your velocity limits, what's your delta B limits, so you can size a pipeline according to your company limits. You get my point? Basically what we are trying to say is that here is the limit for Total. Ask for these limits in your company. You follow me, phase, right? For the course purpose, I will be happy, more than happy, if you do the simulation the same way I did. For practical purpose, I will ask you for doing hydraulic for any pipeline you have in your plant. Just choose any random pipeline, gas pipeline, liquid pipeline. Basically, tell me the boundary limits. What is the pressure? Everyone write after me. The pressure, the temperature, the pressure profile. Let me open 1 minute. And I will do it so I can forward it for everyone. Here, what you will need to do is 1. Define the boundary limit. When we say boundary limit, we mean pressure, temperature, composition, viscosity, density. Two, define pipe line profile. If you have the isometric, will be good. If you don't have it, by your eye, tell me this pipeline is moving straight forward for 4 meters, then go down by half meter, go right by 5 meters, up again by 2 meters. I need a rough, very small isometrics drawing, if you have any of them. Then define your company velocity and differential pressure limitation. Once you have it, you can go and make the calculations. Now, once this three with you, you can use Excel sheets on WhatsApp. It is sent or not? Let me check. It is already on WhatsApp. Can everyone confirm on me? Yes, it is your vision calculation. One for the liquid, one for the gas. I will open it now. Excel sheets on WhatsApp. Then you have the HYSYS model. Depend on what you want. If you want to build the same model I built, I will be happy. If you want to update it according to your plant, I will be more than happy. You got my point, everyone? Hello? And based on that, we are making hydraulics. I will copy and paste all of this. Here we are on work. And here we are. that we are going to do. Now let's open your BandIDs to see what you did. Let me download it. Naja, I will open your BandID. I'm expecting you to explain what everything you say. You're right, okay? Here we are. You can see your screen, your drawing. Tell me. Naja, use the mouse. I give you control. Your mouse is moving now. It's a feed line. Okay. This is a recycle valve, right? Perfect for me. The control level control valve for the separator. For the separator. For the separator. Sorry, I replied to Faiz on WhatsApp. Yes, Faiz, I will send it to you on your mail. No problem. Naja, please, the control valve of the separator. This one. I want to understand how this will control the level inside the separator. Naja, this one. Yes. Perfect. Perfect for me. I'm really happy. Really happy, wallah. You know that actually I will take the control. I will share with you the BNID from the compressor. Let me open it. Hey, where's the share? Yes, let's share. Everyone can see this page? Hello? Everyone can see my PDF? This is what we are presenting as EBC company. MBT box. I don't get it. You asked me to draw a BNID for the compressor skid, and now you give me a MBT box? Yes. Why we are saying this, Naja? Why I insist for the compressor especially? Because it is coming for a vendor. When we are dealing with a vendor, as you can see, let me draw here just to be able to comment. As you can see, this limit is called package limit. This dashed line is represent the boundary limit between me as EBC firm and the compressor vendor. Compressor vendor is responsible to take my gas from here, this type in point, and they deliver me gas here at this tie-in point. Take the gas here with 250 as we speak about before, remember? And they deliver it here to 1100 psi. Remember this, Naja? For process guarantee, the vendor is responsible for which instrumentation to be installed here on side his skid. That is always happen with all light sensors. Do you have a licensor in your plant? Do you have any technology? You have a reactor, you have catalytic cracking if you're working in a refinery, you have reactions if you're working petrochemical. Tell me. Perfect. The boundary limits between you and any licensors is the heat and material balance. which saying that you speak to the vendor saying that to him. I giving you the B equal 250, the T equal number, the composition equal number. Here is heat and materials feed entering, and he is responsible to give it back to you here. You got my point, Naja, Muhammad, Faiz? That's always the connection between the licensor or the vendor and the EPC company. The heat and the material balance, which is critical for every single communication between us and the licensors vendors. So, if this is the case, we have to generate the heat and material balance. If we're sharing back the heises here, we simply can go for report. After we're making all this one, we can go for report. We say create. We have a report one. We add insert data sheet for the feed gas, the inlet, the gas to piping network, the outlet, the condensate outlet, and the water outlet. Once we have all this, we say preview. Then we have the heat and materials balance data, heat and material balance data sheet full. What's coming from the well? Sorry. You see my PDF, right or no? Report review part report 1. You see it? Anyone reply to me? Hello? Guys? You see the material stream from the gas well, right? You see my mouse? Okay, perfect. From here, we can see the heat and material balance for the vapor, liquid, aqueous phase, over the properties, and everything we want to see for the total plant. If we can print it, so I'll keep it. I open it on PDF easier. 1 minute, keep it here. This, so then I need to share. Here is what we get from HYSYS. 14 page describing the heat and material balance or overall process. What we have from the well with all the properties, doing all the properties, the composition we are entering from the beginning. Do you remember it? Mole fractions we added. Then we have the inlet for the compressor, mole fractions, mass flow, going down. What we have the gas for the compressor here. Temperature is outlet of the compressor is almost 167 Celsius because we didn't add cooler after the compressor. Then we have a bar G, high pressure, almost 75 bar G. Then we have a quantity of gas equal 20 million scaff, almost 19 million scaff, which is corresponding to 60 meter cube per hour. And then we have the overall properties here. Then we have all of these compositions down for the liquid, condensate, we can give the same condensate specs to the pump vendor. We simply saying to the pump vendor, we need a pump with to pump the following composition. We will have a liquid composition, the same vapor, pressure, temperature, and flow. And the composition of this liquid is like this one. Here we are. Mole fraction for this is a heavier component, and the physical properties of this mixture is, here we are. Over all physical properties, we need to take a snapshot of it and fill the pump data sheet and the vendor and the compressor data sheet to be tendered out to the vendors to submit their offers. We as EPC companies always we take the output from the HYSYS, inserted it on the data sheet for the pump, for the compressor, and tendering out to the vendors. Please, we need a compressor to do 1, 2, 3 with this data sheet. We need a pump to do 1, 2, 3 with this data sheet. Based on that, we receive the vendor quotations and we evaluate it. We update our materials after this. You got my points? Hello? This is the cycle. Let me share this with you on WhatsApp. Muhammad, can you tell me your password for the team viewer? I think the HYSYS is finished now, right? Muhammad, did the HYSYS finished? Okay, just if it is finished today, text me. I will record this for everyone. It is the same video I sent it yesterday. And everyone if anyone have a problem with HYSYS, just tell me. Okay? Okay, we will meet next week inshallah. We're making our line list. Then we are going to speak about the separator and how we sizing the separator, and we will presenting the final look for the BNID and how we apply the isolation philosophy for the separator, and speak a little bit about the controls. Anyone have a problem? Anyone who need something, tell me. Yes. Muhammad is downloading the HYSYS. Muhammad was not downloading the 10 GB which I uploading to my Google Drive. So you have it, and now I can install it now for you. Okay, we can make this at late, or yes, at night, or you are now ready. Okay, if it is 10 minutes, I will waiting for you. I will waiting for the 10 minutes.